right? So test 2 started off talking about the ideas of correlation, right? And when we start doing examples, I'll go through a lot of these ideas again, right? And then once we had correlation, we use that to help us get regression lines, right, which we use to help make predictions, and we'll talk about those when we do a little example of that. Right? And then from there, we started talking about a different type of spread, right, which was the 5-number summary, right? And then how to do the box plots and how to graph those things. Right? And then the last thing we did was when we first started to take a look at normal distribution types of problems, right, to where kind of we drew our bell curve, put our point on there, found the areas and probabilities from those particular those types of problems. Okay. So those are the ideas we're going to try to run through during our time here. Again, hopefully that is it'll just kind of ring some bells in your head so that when you go back and start doing some more of these problems, it'll come a little bit easier for you. And of course, I'll be around too, just hanging out if you ever need to go over some of these things together, one-on-one or with a smaller group too. Okay. So let's talk about correlation real quick. Okay. So what we had done all the way through test 1 is we just kind of looked at one variable at a time, right? So I gave you a data set. We found averages, we found standard deviations, things of that nature where we just had one variable at a time. The idea behind correlation, we started asking ourselves this type of question, right? Are two variables related to one another? Right? And by related, we used a couple of words in class, right? Correlation as well as causation. Right. Correlation, that was the mathematical formula we came up with, and we came up with that number, I think we called it R, right? Which gave us a numerical measure that was, if you remember, somewhere between, that's good writing right there. Let's see, where that value for R, assuming that we actually did it correctly, would be somewhere between 1 and -1. Right? And the correlation measures, if you remember, what was called the linear strength of the relationship between the two variables. Right? So in other words, if I graphed my scatter plot, right, where we had our explanatory variable on this axis, right, and our response variable on this particular axis, right, we would start plotting these points on here. And if it looks like the points were in kind of a straight line type of a pattern, then we could try to apply these techniques, right? So what we do is we come up with a correlation, find an equation for this line or this model that went through all those points, and would start making predictions from that, right? As opposed to if I had a data set that was nonlinear, maybe some points that look like one of these parabola type of things, then this value for R really was not a very good measurement. Because if it's a linear pattern, like we have over here, that can tell me if there is a strong relationship between the two. But here, it can follow this pattern perfectly so that there really is a good relationship there. It's just when we're measuring the linear relationship, this would be a bad model for regression. Right? Because again, it measures a straight line relationship, not a curved relationship. Okay? So we can do the number crunching to get R, and that will give me what's called a strength in that relationship. And if it follows a line really close, then it's a strong strength. Or if it's, kind of one of these curvy patterns, or maybe I just have random points all over the place, then that would be a weak strength. Right? So strong correlations give me values that are either close to 1 or -1. Right? 1 means it has a positive association, so it's going up. -1 means it has a negative association, so it's going down. And excuse me, and it could be going down kind of slowly. Excuse me, slowly, or it could be going down really fast as well. Right, and if we have really bad strength, then it's kind of close to 0. Right, so for correlation, the sign, the plus or the minus sign, just tells me if I have a positive association or a negative association. Right, by a positive association, that means the big values for the explanatory go with the big values of the response. For a negative association, the big values of the explanatory go with the small values of the response. or vice versa. Small explanatory go with the big values in the response. Okay? So that's what it means to have a positive or a negative association. So that's what the plus or minus 1 could be in our calculations. Okay. All right, then what we can do is we can calculate this number r, and that'll tell us if we have a linear strength between these two particular variables. But that doesn't mean we have a cause and effect relationship. We still have a lot more work that we have to do with that, right? Because we saw an example in class, I think, where we had some type of a plot where it was lemons imported versus pirates or something like that. And it was some type of a really strong correlation that went down like this, which told us that as lemons increase, pirates decrease. Right? So we said that if we just imported more lemons, we could really reduce the risk of piracy throughout the world, which of course is ludicrous. But if we went through the calculations for R, it was like 0.97 or something really big. Right? So just because we have correlation, right, a strong correlation, that's not the same thing as saying we have that causation, that cause and effect relationship. Right? So this is just kind of the first step in trying to figure out if there really is a cause and effect relationship. All right, so that being said, how do we calculate the value for the correlation? All right, so again, the idea is we have two variables, right? We have the explanatory variable, right? And we have the response variable. Right? In terms of notation, we always call this one X and this one Y, but I mean, you can call them anything. Okay? So let's just pick 4 points here and see what we've got. So let's let X be 2, 5, 7, and let's see, how about 6? And the y's could be, how about 8, 7, 4, and let's see, that's 15, and how about a 5? Okay. The first thing that we did in terms of trying to see if there was a relationship on here is we made what was called a scatter plot. Okay. So we have a vertical axis, we said, for the response, horizontal axis for the explanatory. So let's see, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. So we kind of kept these things in pairs, right? The first pair was 2, 8. So I would go over to 2 and then up to 8, which is right there. And then the next point was 5, 7. 1, 2, 3, 4, 5, 7. And then I had 7, 4. And then 6, 5. Okay. So that's what my scatter plot looks like. Okay. And of course we'd have labels on here just to make it look a little bit better, but that's it in a nutshell. Right? And if you notice, it does seem to kind of follow a linear pattern pretty well. So I bet when we calculate this, we get a pretty strong value for R. And since it's going down like this, I bet we get a strong negative value for R. Right? So again, it's going to have that negative association because as X gets bigger, these Y values got smaller. Okay? So let's try to remind ourselves how to calculate the correlation. So let me get rid of this. Okay. All right, so if you remember, the idea is we get standard scores for the X's and the Y's. Okay, so what we need to get our standard score, like if I have some type of an X, right, to get its standard score, I subtracted the mean and divided by the standard deviation of the X's. For the Y's, I subtracted their means and divided by the standard deviation of the Y's. Right? So in this case, let me see, to get the average of the X's, we just add them all up and divide by 4, so that's 20 over 4, which is 5. For the Y's, if you add that up, you get 24 over 4, which is 6. Okay? So we made our charts of the X's, and then to get their standard scores, we looked at X minus X bar. So in this case, X bar is 5, so 2 minus 3 is, or 2 minus 5 is negative 3. That's a 0, that's a 2, and that's a 1. Okay? And then to get the standard score, we divided by the standard deviation of the X's, where in this case, let me cheat a little bit and get a spreadsheet to help me out with this. All right, so the standard deviation of the x's is 2.16. Okay. Okay. So let me get all these standard scores for us. Okay, so it's that minus 5.16. Okay. All right. So for this first one, I took the score 2, subtracted 5, divided by the standard deviation, and that gave me a z-score of negative 1.39. Right. Here I took 5 minus 5 over its standard deviation, which gave me a 0. 7 minus 5 over 2.16 gives me 0.93. And then 6 minus 5 over 2.16 gives me 0.46. Right. So those were the standard deviations of the x's. Let's do the same thing for the y's. Let me see here. I wonder if I can squeeze it in over here. Okay. So the standard deviation of the y's, let me see, 8, 7, 4, 5. Standard deviation for the y's is 1.83 if you do that work. Right? So to get these standard deviations, again, let me write down all the y scores and then get their standard score. So for this first one, let's see, it'll be 8 minus 6 divided by 1.83, which gives me 1.09. Right? And then for the rest of them, if I take 7 minus 6 divided by the standard deviation, I get 0.55. For the 4s, I get negative 1.09. For 5, I get negative 0.55. Okay. All right, and then to get your value for r, if you remember what our process was, is we would take the first standard score for the x's, multiply it by the first standard score for the y's. All right, so I'll take that negative 1.39, multiply it by 1.09. Right? And then I'll add to that what I get when I do the same thing with the second standard scores. So that'll be 0 and 0.55. Right? And then do the same thing for the third standard scores. And then finally the same thing for these fourth standard scores. Right? And then if you remember, when you're done with all of that, what you do is you divide it by n minus 1, where n is just the number of pairs we have here. Right? So in this case, n is 4, so I'll wind up dividing the whole thing by 3. Okay, so that'll be, let me see, 1 over 3 times, and let me multiply these things out for you real quick. All right, so this is negative 1.518 plus 0 plus negative 1.012 plus negative 0.253. Okay. And then if we add all of those numbers together, we get negative 2.783. Right? And then if I take that and divide it by 3, oops. Sorry, hit the wrong button. You get negative 0.93. Right? So if you remember, based on the scatter plot, we thought it would be a really strong negative number, and it is. Right? Now, sometimes depending on how well you draw that scatter plot, it could be a bad picture and it could give you a really bad estimate. So don't rely on looking at the scatter plot. Make sure that you do the calculations and get it. Okay. All right, so before we go on, you all have any questions with how we got that value for the correlation? No. All right, and on test 2, I gave you the standard deviations, so you had to calculate the the averages yourself, but that was kind of the first problem. Okay. All right, so let's go ahead and keep this data set. Let me copy it here. And let's work through the equation for the regression line. All right. So let's see. So the x's, I had a 2, 5, 7, 6, and 8, 7, 4, 5. The averages of the x's was 5. Average of the y's was 6. Standard deviation for the x's was 2.16. For the y's was 1.83. And the value for r was negative 0.97. Right? And if you remember, our scatter plot looked something kind of like this thing. Right. All right. So now the question is, can we come up with an equation for that regression line that goes through there? Okay. Well, with any line, remember, all you need to do to graph it is you need to know the slope of the line and the intercept for the line. Right. So in this case, let's see. I think we called the slope b, if I remember right. And the equation for that was just r, the correlation, right, times the standard deviation of the y's over the standard deviation of the x's. And for the intercept, it was always just, I guess we call that thing a. It was y bar minus b times x bar. Right? So again, you wanted to find the slope first because we actually use it down here when we find the intercept. Okay. So for the slope, let's go ahead and calculate that. So it's negative 0.97 times, let's see, the standard deviation y was 1.83 over the standard deviations of the x's. So I get negative 0.82. And then down here, it'll be y bar minus b. Oh, that should be negative, my bad. So it'll be negative times x bar, which was 5. Right? So let's see, this will be 6 plus 0.82 times 5. I get 10.1. Right. So the equation is y hat equals the slope times x plus the intercept, or bx plus a. So in this case, y hat is just going to be b, negative 0.82x, plus my intercept, which is 10.1. And that's the equation for this particular line. Okay. All right, so again, that is the equation for the regression line. Right? And then if I wanted to actually plot the line itself, remember one of the points that's on there is that point x bar, y bar, right? Which means the point 5, 6. I think I kind of drew it wrong, but yeah, let's just imagine it's right there. 5, 6 would be on it. To get any other point on the line, just plug in some number. So I could plug 4 into this thing, right? So let's take y hat and plug 4 into it, and that will give me negative 3.28 plus 10.1, which is 6.82. Right. So I've got 5, 6, and then I've got this point 4, 6.82. Okay. So now I could plot those 2 points and then connect my 2 points to draw the line for the regression line right there. Okay. All right, so any questions on finding the equation for the regression line? And just like almost anything else we've been doing in this class, it comes down to knowing the formulas. Right? If you know the formulas and how to use them, it's not that bad of a process. You just have to know how to use these things and how to actually, not make little mistakes here and there. Yeah. All right, now one of the big things people use regression lines for are to make predictions. Right? Like I could say, all right, what happens if I plug 8 into my function? What number should I expect to come out? So in other words, if I plugged 8 in here, what number should I expect to come right back? Right? Well, what you do is you just plug 8 into your equation, and you get negative 0.82 times 8 plus 10.1. So that is negative 0.656 plus 10.1. Whoops, I put the decimal in the wrong spot. My bad. 42584. So it's like 3.58 or something. Again, I'm not sure, but that point right there would be 8 comma 3.58. And that one might be off. Might want to double check it and see. So my best guess would be that if I plugged 8 in there, I expect 3.28 or 3.58 to come right back out. Okay. Or 5.4 maybe. All right. Now also, one bad thing about making predictions, there's this word we used a few times, extrapolation. Right? Remember, these predictions are only relevant for scores around our explanatory variables. Right? If I asked you to make a prediction for what happens when I plug 50 into this thing, then yeah, we can plug in 50 and get a number, but it could be completely bogus, right? There's no reliability to it at all. So extrapolation occurs when you try to make predictions outside your data set. Okay? So yeah, so 8 is kind of close, so that's not too bad, but 50, yeah, that's pretty far away. So let's not worry about that one. All right. Any questions then about finding that regression line? Anything at all I can remind you about? Anything I've confused you about yet? Excellent. Okay, let's do a couple more things here. 2 more ideas that we had on this particular test was our 5-number summary and box plot. All right. So if you remember your 5-number summary, let me see, 5-number summary. Okay. Right. And let me give us a data set. And remember, you want to order these things if you haven't already, but let's assume I've got an ordered set here. Let's say 11, 15, 17, 17, 19, 23, 25, 27, and 30. Okay. For your 5-number summary, 2 of them you get right off the bat. You get your low score, and you get your high score. Right. Now for the other ones, you have these quartiles, Q1, Q2, and Q3. Q2 is just the exact same thing as the median. So let's go ahead and find that one. All right. So here I have 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. And if you remember, the median is a number that falls right in the middle. Right? And the way you find that is it depends on if you have an odd or an even number of scores. So if we have an odd number of scores, the median occurs in spot n plus 1 over 2. If I have an even number of scores, we take the average of spots n over 2 and the very next one, n over 2 plus 1, whatever it happens to be. Right? So in this case, since I have an odd number, it occurs in spot 9 plus 1 over 2 or 10 over 2, which is spot 5. So I would go over here to spot 5, right there, and that is my median. Right? So in this case, I get a 19. So now for Q1, it's the median of all the scores below the median. Right? So I'll look at those numbers right there. In this case, I have 4 scores. That's an even number. So I divide it by 2 to get the first spot, and then add 1 to it to get the next one. So in other words, use this number and find their average. So the average is 15 plus 17 over 2, which gives me 16. Okay. And then for Q3, look at all the scores above the median and find the median of that list. Same thing, we've got 4 scores, so I will average out those 2 scores right there, 25 plus 27 over 2, which gives me 26, and that's going to be Q3. Okay. So that's my 5-number summary. And once we had that written down, we tried to make a graph of it by using what was called a box plot. And if you remember a box plot, it goes something a little bit like this. We would make a horizontal axis. In this case, we had numbers from like 11 to 30, so maybe I could start off at the number 10, and then 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, right? So we can go up maybe by twos here. All right. And the way we did this box plot is we built our blocks around the two quartiles, Q1 and Q3. So I can draw a line here at 16 for Q1, draw a line at 26 for Q3, and then make a box based on those particular scores. Right? And remember, you want to label these things so the reader knows exactly what values that you're using. Right? We would mark the median as well. And then we had these whiskers that went down to the low score, which in this case was an 11, and up to the high score, which is 30. Right? And that told me, or that gave me my picture of this particular 5-number summary. Okay. All right. Now, one of the reasons why we like the 5-number summary so much is it helps us find outliers. Right? And if you remember the idea behind outliers, we set this kind of a low fence and a high fence, and everything inside these fences was good, but if you were too high, you were a high outlier, or too low, you were a low outlier. So we need to figure out ways to get equations for these fences. Right? And we found a pretty good way to do that. Right? We used what was called the interquartile range, the IQR, which is just Q3 minus Q1. So in this case, that's 26 minus 16, which gives me 10. All right. So to find the high fence, what we did was we took Q3 and we added 1.5 of these IQR values. Right? So I took Q3, which is 26, and I added 1.5 times the IQR, which is 10. So that's 26 plus 15, which gives me 41. And then to get this low fin, so the low boundary, start at Q1 and subtract 1.5 of these IQRs. Right? So in other words, I'd start at 16 and I'd subtract 1.5 of these IQRs. So that's 16 minus 15, which just gives me 1. Right? So for outliers, we have boundaries from 1 up to 41. Everything in between here is okay. Everything outside it is an outlier. Okay? So if you notice, my low score is 11, it's in there. My high score is 30, it's in there. So that says I have no outliers. Okay. All right, so I don't have to change the box plot at all. So just in case there is an outlier, let's do this. Let's assume that 30 was an outlier. Then what we would do for my box plot is I would go back to it. Okay? And at 30, I would put a little star to represent an outlier. And then the whisker would then come up to the next non-outlier score, which in this case would be 27. Right? And that's how we designated outliers on our box plot. Okay. All right. And if you remember, why are outliers so important? Well, if you remember, outliers really mess up the mean, which means they really mess up the standard deviation, which means they really mess up the correlation. Right? So if you have outliers, it's really suspect to use any of those. Right? So if you do have outliers, remember we would use the median as my measure of center and the 5-number summary. Right? So if we have if we do have outliers, you use those measure of spreads. And if you have no outliers, that's when you use the mean and the standard deviation. All right, so going back to this, any questions on how we calculated that 5-number summary or did the box plot with and without outliers? How we found those fences, everything else okay? Well, when everybody's talking at the same time, it's really hard for me to hear, so I'm just going to assume that it's okay and just move on. All right, so the last thing we saw in our particular test 2 was stuff with normal distributions, right? And this was just the introductory stuff, right? To where we had our normal distribution, we knew what our mean was, so we'd find some type of a number and find the probability of it being too high or too low, one of the two. Okay, so let's work through the problem that we've got on our test here, just so we can see it. Right. So in this case, we're measuring ball bearings, and it says these have a normal distribution with a mean of 5 millimeters and a standard deviation of 0.02 millimeters. Okay. And let's see, the question we ask is this: what proportion has a diameter more than 5.03? So in this particular case, right, the average is right there at 5. We want to find the probability of getting 5.03 or more. Right? So we just took our z-score to be 5.03 minus 5 over 0.02, right, which is 1.5. Right? And of course, I don't have my book open. So let me see here. Oh, yeah. So if you look up 1.50 in the book, you get 0.9332, which again is the area from that point on down. So if we subtract that from 1, I get 0.0668. Right? So the question says, what proportion has this diameter? The proportion is 0.0668. If I ask for percentage, then that would be 6.68%. Right? So make sure you read through the problem to see which type of answer that it's asking for. Okay. All right, and there's a couple more examples on there in that test that kind of go through the exact same process. Okay. All right, so any questions over what we're doing here on test 2?
All right, so again, if you all need any help at all, make sure that you contact me. We can just talk, we can do it through email, we can do it however you need to do it to make sure that you're doing okay. Just let me know what I can do to help you out. All right, you all have a great day. I will talk to you soon. Bye.